This specialized facility manages the precision structural engineering of the L0 series. This specialized long-nose geometry requires advanced composite forming and rigorous verification.
この接合部分の設計ですが、もう少し強度が必要だと思いますね。
それならね、こちらの素材に変えてみてはどうでしょうか。
それでいきましょうか。
We begin the process by examining the foundational structural engineering of the chassis.
Precise engineering blueprints define every structural coordinate of the L0 series chassis.
High-grade aluminum alloys are selected for their optimal strength-to-weight ratio.
Rigorous material verification ensures the structural integrity of the high-speed maglev frame. With specifications verified, the raw materials are moved to the primary welding stage.
Primary chassis construction begins by securing heavy-gauge aluminum beams into high-precision jigs to ensure absolute structural alignment.
As these automated sequences continue, the primary frame gains the necessary rigidity required for the complex integration of maglev components.
Vertical reinforcement ribs are now integrated into the primary frame to complete the three-dimensional structural volume of the chassis.
With the primary frame verified, the structure is prepared for the specialized integration of the aerodynamic nose section. The signature 50-meter nose section begins fabrication within a specialized mold to ensure absolute aerodynamic symmetry and structural precision.
The base alignment looks good. We are within the specified tolerance.
Confirmed. The laser scan data matches the blueprint.
Every millimeter of the nose curvature is verified against digital CAD models to eliminate drag-inducing surface imperfections during high-speed travel.
Surface continuity is paramount, as the long nose design is specifically engineered to suppress the sonic boom effect in tunnels.
Once validated, this critical aerodynamic component is staged for integration with the primary high-speed maglev chassis frame. The fabrication begins with niobium titanium alloy wires, selected for their superior performance in generating powerful magnetic fields for levitation.
Precision winding is critical, as any structural deviation can affect the stability of the superconductive state during high-speed operations. Rigid structural supports are integrated to withstand the immense electromagnetic forces generated when the magnets are fully energized.
These precision-engineered coils form the core of the maglev propulsion system, awaiting final assembly into their cryogenic housing modules. Individual coils are precisely seated into high-strength mechanical housings to form the foundation of the functional maglev magnet module.
All parameters are within tolerance.
Good, let's move to the next one.
Strict mechanical tolerances are maintained during assembly to ensure structural integrity under the high-stress environment of magnetic levitation. Every module undergoes a rigorous static verification process to confirm that all electrical and mechanical interfaces meet high-speed rail standards. With the core magnet modules assembled and verified, the components are ready for the next stage of system integration and cryogenic housing. The structural frame now transitions into its final aerodynamic form as high-strength alloy shell panels are meticulously integrated.
Right there, slowly. Got it? It's in. Alignment confirmed.
Minimizing surface gaps between the shell and frame is vital to reducing air resistance during future ultra-high-speed levitation runs.
See this section here, the hydraulic line routing.
It doesn't match the current assembly. Why is that?
It was updated in the latest revision. Let me show you.
The integration process demands absolute geometric symmetry to maintain stability and prevent aerodynamic buffeting.
The panel alignment is precise. No surface abnormalities detected. Recording the data now.
Advanced assembly jigs hold the lightweight alloy skin in tension, ensuring the outer shell contributes to the overall rigidity of the vehicle. With the aerodynamic shell fully integrated, the SCMaglev prototype moves closer to internal system routing and final technical fit-out.
With the shell integrated, technicians begin the complex process of routing high-voltage power cables and signal lines through the chassis.
Look straight from here. Okay, locking it in now.
System separation is strictly enforced, isolating power delivery from signal and pneumatic lines to ensure maximum operational safety and reliability.
Specialized insulation and flexible conduits are utilized to protect vital systems from mechanical vibration and thermal fluctuations during travel.
Every cable run is mapped to high-precision engineering standards, ensuring that internal routing does not interfere with the vehicle's aerodynamic or structural integrity.
Comprehensive labeling and systematic routing allow for efficient maintenance and diagnostic checks throughout the life of the Maglev vehicle.
The successful installation of internal subsystems provides the final structural and electrical foundation before the cabin interior moves toward final finishing. The magnetic bogey construction begins with the positioning of specialized levitation modules, engineered to provide powerful electromagnetic lift.
We are within tolerance. Verified. Lock it down.
These non-wheeled support units are designed to generate high-intensity magnetic repulsion for stable vehicle lift without any mechanical contact.
Face alignment is stable on all fronts.
Good. Clear for integration.
Absolute symmetry of the magnet modules is paramount to ensuring balanced magnetic forces and smooth lateral stability during levitation.
Structural integration proceeds as the vehicle body is mechanically mated to the magnetic bogey, establishing a direct load path for electromagnetic lift. Maintaining precise mechanical clearances is essential to ensure that the air gap between the magnets and the body remains constant during operation.
Alignment is stable at 0.2.
Confirmed. Proceed with fastening sequence.
With mechanical integration complete, the structural assembly of the SCMaglev is verified. Surface treatment begins with a multi-layer electrostatic coating process, essential for long-term corrosion resistance and aerodynamic surface uniformity. Precision robotic systems ensure a perfectly uniform application, maintaining strict tolerances for coating thickness across the entire 10-meter body section. The final multi-layer finish not only protects the structural alloy, but also minimizes air friction, a critical factor for ultra-high-speed efficiency.
The experimental maglev profile is finalized, meeting all aerodynamic surface quality standards.
Static testing begins with the integration of diagnostic systems to verify the integrity of all onboard sensors and safety actuators. Levitation gap sensors undergo rigorous calibration at rest to ensure millimetric accuracy during future magnetic support operations.
We have a gap reading of 4.8. Run the cycle test.
Cycle complete. Force checks out within safety parameters.
Braking systems are verified at rest, measuring clamp force and actuator response times within strict factory safety tolerances.
Laser synchronization complete. The gap remains constant.
Noted. Proceed with the diagnostic cycle.
Signal integrity checks confirm that all diagnostic data paths are clear and free from electromagnetic interference.
System verification is conducted in a controlled environment, ensuring all diagnostic signal paths and sensor arrays meet strict operational readiness standards.
Static verification is complete, confirming all systems meet experimental safety requirements. Manufacturing and static verification are complete, concluding the vehicle's factory phase.
このセクションは問題ありませんですね。
はい、確認しました。で
では2商用しますが、
Behind every breakthrough stands quiet dedication and respect for the craft.
The journey forward begins with mastery, vision, and trust in what comes next.
NextGen Machine Works, building the impossible. Subscribe to join the future.